Introduce you. Hello, everyone. So today, Schuchen will speak to us about cyclic homology and algebraic K-theory.
Thank you, everyone. Thank you, Julie. And I apologize for the technical difficulty here. Anyway, let's start. So, algebraic K-theory is a very important invariant in many fields, including algebra, topology, algebraic number theory, and so on. Let me introduce a little bit of algebraic K-theory. So suppose X is a CW complexes, and suppose it's dominated by a finite complex. Well, that means you have X, you have a map to F, and you have X, and this composition is homotopic to identity on X. Then such complex is called finitely dominated complex. Then you can take the chain complex on the universal cover of X, and you can prove that its chain homotopy to a finite complex consists of finitely generated projective modules. Okay. And then you can define what's called Wahl's finiteness obstruction. So it's just taking the alternating sum of the class of PIs in the complex that you have, and it's going to give you a class in K0, and we know like we can take K0 to split it into the sum of K0 of the base ring Z and the reduced K0, and the reduced K0 part of your class X is called the Wahl's finiteness obstruction, and it's known that suppose the complex is actually equivalent to a finite complex, then this will vanish. Okay. Okay, and the second example of in algebraic K-theory, that's called Y-height torsion. So suppose you have a homotopy equivalence of finite complexes. So this is homotopy equivalence. Finite complexes. Then you can define the Y-height torsion in pi one of this complex. Okay, and what is that group Y-height? It's the co-kernel of the inclusion of the group across negative. You have negative of the part in the group ring, and you take the co-kernel of this inclusion. That will be the Y-height group of this pi one. And how to define this Y-height torsion? Well, if you consider F, you lift it to the universal cover. So and then you take chain complexes, then you have a chain homotopy equivalence between F tilde and L tilde. And this will you take a cone on this map of chain complexes, you're gonna get a cyclic finite free chain complexes, and then you can define the Y-height torsion to be the Y-height torsion of this cone of chain complexes. Okay. Is there any questions about those two? Okay. I'm not sure if you can hear me or like I can hear you.
We can hear you just fine. It's all
Okay.
good.
Oh, okay, sure. So, in short, K-theory is a functor from you can consider rings to abelian groups. It can be defined for more general things. For example, you can actually define it for infinite categories. And yes, so when you have it's a covariant functor. So if you have a map of rings, you have the uh, value of kr mapped to ks in the correct way. Okay, and what we were interested in calculating was kind of the wrong-way map on a K-theory, which is called a transfer. And so it occurs when you have, oh, sorry, I read this notes kind of backwards. So suppose you have a ring map such that S become finally generated and projective over R. And then you can define the finite projective modules over S to pull it back to be a module over R. So you get a map on the category from CS to CR. And so you have a wrong-way map on K-theory because the K-theory is defined using the module category. Okay, you can just consider every element of S here is actually acting on itself on the right-hand side as a matrix. Okay. Any question about this? Okay. So why do we want like K-theory of for like transfer maps? Well, it came from some consideration from like geometric topology. So suppose you have a perfect fibration, E to P. This just means the fiber is finally dominated. Yes. In other words, the fiber is actually dualizable in the stable homotopy category. So you can find its dual and define the transfer. Define the trace. Sorry, define the trace. And then you can consider the infinite suspension on loop of those spaces. That's actually a map of ring spectrum. And you can show, okay, suppose the fibration is perfect, then this map of ring spectrum will make infinite suspension of loop B perfect over infinite suspension of loop E. Okay. And so you can take K-theory of this ring spectrum and define the wrong-way map, the transfer. Okay. And it's actually just the Waldhausen's K-theory for spaces. You can define it, you can consider it as a ring spectrum and define this K-theory using the category of modules on that, or you can define it just using the normal retractive space definition of A-theory. They're the same. Okay. So it's known that the A theory of a space will split into the Q of B. So this is also just, you can denote as Q of B. And product with the Whitehead diff, just another another spectra which you can consider as generalization of like a Whitehead group. So we know that okay, then this is a map between two components and another two components, and a theorem of Malkowicz and John Lind has identified like the map from the component 1 to 3 is actually given by the Becker-Gottlieb transfer. So you can just infinite loop the suspension spectrum of B and suspension spectrum of E. And yeah. And a theorem of Dwyer-West-Williams saying, okay, suppose the vibration is actually a smooth fiber bundle, or say it's fiber-wise equivalent to a smooth fiber bundle, then the component from 1 to the component to 4 will actually vanish. It will be 0. So it's actually telling you some interesting stuff in geometric topology. Any questions about the statements? Okay, so that's basically the motivation we want to study, like the runway map on K-theory of things. Okay. So I'll introduce a little bit of this transfer thing. Its first occurrence is actually in Schur's transfer in group theory. So suppose you have a group G and a finite index subgroup H. Then you can define this transfer map from the abelianization of G, the abelianization of H. And it was later identified as the restriction map on first homology of group G to first homology of group H. You can find reference for this from Serre's local field. So local Serre, I think it's page 120. You can find reference for this. And so it was so you can actually define this just using classifying spaces of the groups, and we know that group homology is actually the homology of classifying spaces. And when it was in that case, BG over BH, sorry, excuse me, not BG over BH, but you have H include to G, that induces the map from BH to BG. And if you take just a vibration replacement of this one, this will be just a finite sheeted cover of N covers because G is sorry, H is of index N. Okay, so this is a N covering. And so basically, this is a special case of what's later found called Becker-Gottlieb transfer. Yeah, so the Becker-Gottlieb transfer is defined for all vibrations of where the fiber is finite dominated. Okay. So it's the runway map because you can think about this one as generalized homology theory. So you can see, well, if it's homology, it should be tau should be the natural map should go from homology of E to homology of B. But suppose the vibration is actually very nice like that, then you can define the runway map. And this Becker-Gottlieb transfer shows up in a proof, a shorter proof of the Adams conjecture, and that's in 1975. Okay. And we know that suppose you take the transfer and you take the projection, it actually gives you the Euler characteristic of the fiber. Okay. Okay, then we can define transfers on Hochschild and cyclic homology because they're much easier to evaluate and see than K-theory. Okay, so Hochschild homology of a ring A is given by a complex where the zeroth term is one piece of A. The first term is A tensor A, and the map is given by, well, the map is given by A tensor B sends to AB minus BA. Okay, and the map, for example, so from A tensor B tensor C here, it will send to AB tensor C minus A tensor BC and plus CA tensor B. Okay. So that's Hochschild homology of a ring. And to define cyclic homology for the ring, okay, you can just take this complex CHH and build a double complex and using this map where the T is actually just the cyclic permutation. So T of A0 tensor up to AN is -1 to the N of AN tensor A0 tensor -1. Okay. And this N operator is given by 1 plus T plus T squared plus T to the N. Okay. And this CHH hat complex is given by, well, if you take the CHH complex and you just disregard the last phase map, and that's that will give you a this CHH hat complex, and it's actually contractible. So yes. Okay, so yeah. I'm sorry, probably. Is this definition clear for cyclic homology? This is cyclic. Oh, okay, so I'll move on. And so suppose you have a map from A to B, such that B becomes perfect over A, then you can define the transfer on Hochschild homology by so-called the Book's multi-trace formula. Now, so how the way to do that is, okay, if you take a tensor of elements of B, well, because B became perfect over A, so you can consider, okay, an even easier case, that is B became just a finite free over A. Then each element of B is acting on itself on the right by a matrix. So this this tensor of elements of B became a tensor of matrices in A, and then the Book's multi-trace formula will give you this map by tensoring the elements from those matrices. You can see the index, they have their like circle around it's I0, I1, and then the next thing will be I1, I2, and the very last element here will be chosen from the I0's column. And okay, so yeah, oh, sorry. Oh, sorry, sorry, this is yes, nodes is kind of, it's mapped from R to S, so S became perfect R. Yeah, just to make the nodes consistent. Okay, so basically, yeah, elements in S will become matrices in R, and you can take the Book's multi-trace. Okay. And after you define it on the Hochschild complex, you can actually define it not only for Hochschild homology, but you can also define it for cyclic homology, because the complex is given by taking the Hochschild complex and make it into a double complex, basically. Okay. So let's just take the example where you have a finite index subgroup. Then the group ring K of H, including to K of G, will be such a map. So G became actually a finite free KH module. Okay. So in that case, we can calculate what the Hochschild homology of those rings are, and this is a theorem by Dan Berglia in '85. It says Hochschild homology of a group ring will decompose according to conjugacy clauses. Well, this is conjugacy clauses of G, and for it will split into a group homology sum, and this G is actually G sub G is the centralizer. So centralizer. Okay. And cyclic homology of this group ring will split into still according to conjugacy clauses, but in this case, there's a difference between conjugacy clauses of infinite order and conjugacy clauses of finite order. So basically, if G hat belongs to G infinite order, that means the order of G is infinite. Okay. So for infinite order, it will become sum of group homology of this NG. Well, NG will be just G minus the subgroup generated by just G itself. Okay. And for for finite order conjugacy classes, it will become a homology on B and G cross B S1. So that's the classifying space of the group S1, also known as CP2. And it will be so this is actually a fibration where this is the fiber and this is the base and this is the total space. Okay. Yeah. So in the case where K is the field containing Q, well, you can just consider the homology of just this product here. Okay. So a theorem by Christian Schlicker in 98, he had calculated what transfer on Hawkesbury homology looks like. Okay, so it's splitting in according to the conjugacy classes to actually group homology transfer, like in the beginning we talked about in the Schur's transfer in group theory. Okay, and so I have identified what the transfer for cyclic homology is for in this case. So yeah, it's given by this formula. It basically means suppose the conjugacy classes that doesn't contain each other, the transfer will give you nothing, and it will be group homology transfer. Suppose it's infinite order, and it will be the group homology transfer tensor with the homology of BS1 in K. And for this one, we do need the assumption where K contains Q. Okay. And suppose you want to do more generally, a general K, you can also do a algebraic proof for this by using a cross module. Okay, because basically G maps into G. This will give you a cross module structure that you needed to calculate. But of course, cross modules homology is in general harder than group homology to write down. So it's still an exercise to write down a algebraic proof for this. Okay, so yeah. So why do we move on to graded algebra and differential graded algebras? That is because we find out that you have the K-theory transfer. You want to study K-theory, you have the map to HH or HC. But actually for group ring, you have the assembly map, which is take BG, smash with K of a point to, K of, or K of K to K of BG, sorry, K of kg. And you also have just the assembly map for could be HH, could be HC, negative or positive. There's a negative cyclic homology. K map to the corresponding theory on the group ring. And basically the assembly of the say the group is actually not very interesting. What's interesting is actually the map on the base ring. So yeah, so our original goal was actually failed because of this. Yeah. Anyway, so let's move on to graded algebra and DGAs. So let's do a very easy, very simple transfer map. Well, suppose the DGA is generated by just one generators, where X has a degree of M times L, and Y has degree just L, and X is sent to Y to the, sorry, it should be Y to the M. Okay. Suppose it's in that case, then ky will become a so-called semi-finite module over kx, and we can do the transfer there. And we can actually calculate the Hochschild homology for such differential graded algebras, and it's given by this simple formula. The only difference is when you have the degree of x is equal to 1, then you have a k mod 2 complication there. Yeah. And so on the Hochschild homology, what does this transfer looks like? It looks like this. It's given by this formula. K just sent to m multiples of k there. And so because we have this calculation on Hochschild homology, well, you can do it on cyclic homology, and you can also do it on negative cyclic homology because this Hochschild homology computation, because it's just a double complex. You can use the spectral sequence, look at the E2 page, and read off the according transfer on cyclic and negative cyclic homology. Okay. Sorry. And so there's also the theorem of Thomas Goodwillie. It's saying that suppose you have a ring, could be a simplicial ring in this case. Well, it could be a DGA. So G Goodwillie. This is 95. Sorry, not 95, but 85. 85 or 86. 86. It says that suppose you have a differential graded algebra A to S, such that on the pi 0, A, or other words, H0. Sorry. Is a surjective and has nilpotent kernel. Nilpotent kernel. F. Then the relative cyclic homology rationally is the relative K-theory rationally is isomorphic to negative cyclic homology of F. Relatively, they're the same. Okay. So you can use this theorem to do the case that we had before, which is K bracket a single generator at degree n, and because suppose say n squared is 0, then K map to K. Well, on degree 0, it's just K to K, so the kernel is 0. So of course, it's nilpotent. So you can basically read off the K-theory of such DGA just by looking at HC of this, of course, rationally, and HC, so HC rational. And so yeah, so you do have the calculation rationally for K of X. Okay, and so we have specific topological examples for this map to calculate the transfer. So you just take the Hopf map from S3 to S2. If you loop S3, well, it will be and loop and suspended. It will be a ring spectrum where you have like a non-trivial homology starting degree 2, because loop of S3 it will lower the degree, right? And for S2, you can also do that. So you do have a map of ring spectrum, and this is a perfect map. And then you can just rationalize this map of ring spectrum, and became just this map. Okay, so K of X map to K of Y. Okay, and you can use that to calculate the transfer on negative cyclic homology of this map of DGA. Yeah. So it will show that so I'll tell you that this K of Q Y map to K of Q bracket X tensor Q. So the map tensor Q is actually 0. So we do calculated just a simple example of this transfer map on K theory. It's given by basically 0. Okay, that means the K theory transfer rationally doesn't give you interesting variance, and it coincides with the theorem that we talked in the motivation, because okay, where is the Dwyer-West-Williams theorem. It says that suppose the bundle is a smooth bundle, then the map from 1 to 4 is 0. Well, of course, the map is 0 as we find out from the S3 to S2 case. And we know the Hopf vibration is a smooth fiber bundle. So yeah, that basically confirms what this theorem was saying. Okay, do we have question about this? Okay, there's one thing I do want to mention, that this theorem is actually interesting because you do have fiber bundles, that is S3 over, I think it was, okay, I couldn't remember on top of my head how this bundle was built, but it was a bundle with topological S3 manifolds. So it's a topological fiber bundle with the topological manifold S3. Okay, but this is called F. But transfer on this, so tall F, which is a theory of B to a theory of F. The component from 1 to 4 is actually non-zero. So this tells you something like really strong, because it tells you that this bundle cannot be smoothed. And it tells you even more that you cannot even find any homotopy equivalent smooth bundles to replace this F bundle. So yes, this theorem is actually non-trivial, despite what we find was a trivial case. Okay. I think I'll stop here.
Thank you very much.
Yeah.
Is there any questions? You're welcome to either just unmute or write in the chat. I'll
Okay.
read it. If anyone wants to ask a question. Otherwise, Zach, can you end the recording?
Okay.